let's start. And I think we will start from assignment 3, right? I already have assignment 3 file here. You can see what assignment 3 do is do a nonlinear analysis with like this. So I will copy the file of assignment 2, assignment 3, and to a new folder here. Right, not working. Okay. So yeah. Okay, some folder. So everything about reading wave from file, output, plot, all the things is same. Numeric beta method is already there. So and also I will need to prepare something. For example, or okay, let me see it. Or requirement of assignment 4. Or a requirement of assignment 4. Okay. I will show it in another window of assignment 4. And also I need something about or explanation about response spectrum. And I need my stat. So all the equations there, you can see it later. So all the assignment, all the equation, most important equations, all here, right? And so I will start from assignment 3. So I will change the folder name to. I will change my main file's name to rename it. Assignment 4. Okay. Assignment 4. So I imported wave. I think all these things is about spectrum, so I will just delete them. Delete them. So this is the wave we did before, right? This is assignment we did before. So we just citing some waves, cite some structure model, and do some nonlinear calculation. So today I will try something new. I will start a new class, which is named spectrum. Okay. So firstly, I will create a new file and save them as a spectrum. Okay. So I'll save class. So firstly we need like everything we need init, and self, right? So we can init start it without anything. Let's start with some basic setting. Start from 0.1 to t end until say 110 0. T maybe say empty. Okay, say empty. So I will let self dot ts equals ts. So self dot te equals to te, and self dot t equals to t. So I will put everything, a lot of things more there if we need. For example, dt, but maybe some dt or something. dt, okay, something like this. And firstly, we need a design spectrum, which is a very typical one. So we'll define a new function. The spectrum. So we just give a self of t. So they will setting all the things for us. So remember, the assignment tell us what is the assignment. Where's the assignment? Where's your assignment? Okay. The assignment told us what is the design spectrum, right? It will equals to this is Japan's design spectrum. So we will give them SA equals to 2000 in unit Gao, of course. Sorry. Okay. Let me SA equals empty list, and we'll do a for loop for ti in t, right? So firstly, I say dot append to 2000 append. Should be 0. Actually, it should be 0. And if so, I will put an I because 0. Yes. Oh. Put it back. Yeah, let's need to do this one. So SI is a if ti is smaller than t end and then ti larger than ts, then I will say SA I equals to I don't need to SA, just say SA I equals 0, and I say I equals 2000 because between them it's 2000, right? Between these two is 2000. So, but if ti is smaller than 0.3, and I will like SA I equals to, due to this equation, 4463 multiple t, so 2.3, right? 2.3. And if ti is larger than 0.7, so I say I equals to this equation, right? 1, 1, 4, 4, 4, divide t 5, 3. Just same with the equation. And I will let SA dot append SAI. Okay. Oh, something wrong. Syntax. This one maybe. Okay. I think 0 didn't used. Yeah. That's true. TETS. Okay. So T equals self. T and TS will be self TS. Okay. And I will give them a return SA. Okay, so if we have if we setting something like this, and we can firstly show input kinetic waves. Okay, so until here is the same thing. Until here is the same thing. And I will firstly import spectrum from spectrum import spectrum. Let's say, okay, nonlinear simulator. This time we didn't use nonlinear simulator anyway. So let me say as a target is spectrum, right? Which initiator we need to decide this one? This one. So we say dt equals to wave dot fs 1 divide. So it's dt. Ts is what we set it here, and Tn is also we set it before. And the T is what we need to decide, because the theory is that we have a response spectrum and we have a design spectrum. We compare them and use Fourier transform to adjust every period component, frequency component. So the response spectrum's T should be same with the Fourier transform spectrum. So what is a Fourier transform spectrum? We need to see design a T and F. So actually, the omega zero is T0 is basically the total design, total length of the wave. We know that the wavelength is n is this length, and so we cut off the length. Okay, we cut off the length here, like this. It start from 1,500, but finished with 4,069, which is length is a little bit longer than before we considered. So we need to check out what is Python FFT's function. So this page is in Japanese, so but you can check out other things in English. Here they give some quick function about the frequency of Fourier transform. So line space, no, that's not what we want, source code. See. So what they get is every time they increase from 100 frequency, basic frequency, and time is n. So let me see what this can do for us. What this can do for us. Okay. This is 4,000. dt is 0.01. Okay. So print. Well, we have frequency here, right? Have frequency here, right? Yeah. So you can see frequency is like this, increasing like this. So first is 0.242, right? So Q 1 this is this value. So what is print 1 divided this one is 4.95 because of the total length of the earthquake is 4.95. So the actually they are increasing with the interval of total length of the wave. So we can use the same equation to decide what is the wave dot length dot n, and same thing with the wave dot frequency. So we can get our frequency like this, and we can get t equals to 1 divided by f frequency. So what's wrong here? I think here is should be like this. So I think it should be wrong like this. dt not defined. Okay, where's dt? Oh, yeah. So the dt should be 1 divided wave dot fs. So let's try this one. Okay, I think it works. So I will plot. Did we have plot? Oh no, we didn't have plot. So let me have this one. PRT dot plot dot t sa t, and yeah. Oh, we don't have them. Oh, let me see what is t here. T. Oh, crashed. Very, very rare to see spider do it like this. I think maybe because T, we didn't get the T properly. I know. Further, let me find my file. Oh, program. Here is it. Okay, so let me see my T. Oh, the first one is not working very well, I think. So, okay. Let me see. But we should not, because the first one is 0 component. It should be very long. So I will be 1 to end. Okay, so let me try again. So T, so actually T is 0. It should be a constant component, so it should be very, very long. So I will say, yeah, because this one, because very, very long time. So let me see what's wrong. Okay. So yes, it's look like this. Look at this. So let me plot it again. Float object is not support item. Plot app. It now works. So what's wrong? Not support item assignment. Okay, it now works like this. Okay. Then whatever. Maybe it's not work for NPy. Okay, I will copy this back and plot T and SA T. Let's see what's going on here. Oh. Still not working. Why? Should SAT. But have shape and 1. Oh. Arrow XY must be the same shape. So let me. Very difficult, right? So first let's print shape. SAT. Oh, okay. Oh, they didn't get the spectrum yet. So, okay. let's say spectrum equals this one, and I say T equals to spec dot design spectrum. What we need is wait a moment. What we need is set from T. Right? We need T only. TI's rule safe. Not support. Wait a moment, I will check Python if and okay. We should just use and. Sorry. If we here we just use and. Still not working. Why? Anything wrong? Float setting array element with a sequence. So, what is SA right now? SCT is list, and T is float. Oh, okay. We should make it to NP array. So this one. Try again. No, not working. NumPy module. What is spectrum returned? I think return SA should be list. Okay. Really not working very well. So let me just plot like this. Nothing. Number. Something like this. Oh, okay. I think something wrong here. SAI equals 0. So let me plot. Let me print SAI. See what's happened there. SAI should be 0, but somehow it becomes an array. Let me try this. Okay, it works, but it's not working like this. Oh, I'm so sorry, it's with TI. Okay, that everything should works, I think. Okay. And I will try to plot this one. Yes, it should look like this. And I will plot it as semi-log x, and it should like this. And I will x limit. Sorry. Matplot lib x limit. So remember, we will need to limit it like this. Okay. I didn't remember I did it so complicated. Let me say solver. I'll have something plot. Just show solver, I think. We plot something better. No, we didn't use it yet. Okay. Then this time let's use limit. Let's use limit like this. Okay. Yeah, T. Let's use TS and TD. Right. I need to do it like this. X equals to. Still not working. Why? Not able to unpack. 2 got 1. It's not working. Why? So strange. Size. Try something else. Okay, this is maybe simpler. This may be simpler. X limit TS T be range. Okay, so design spectrum should like this. Okay. So another thing is to calculate response spectrum. Okay, let me go back to the spectrum. So basically, we will define a design spectrum. Oh no, sorry. Response spectrum. We will need a self, and we need AG, and we need DT, and we need T, right? So, okay, and we will say SA equals to this empty. And, for Ti in T, get omega equals to 1 divided by Ti. And oh, we also need setting of H. And so we will need a new mark beta method. Fine. New mark beta method, which is new omega H AG dt. So we will call them if so SA equals empty okay, SA equals 0 first, and return SA, and we will if Ti is just like this, just like this. I will give them SAI equals new mark W H A G dt. And if not, it should be SAI equals 0. And I will SA dot append SAI and finally we will return SA as I've been asked. So we also need a function to firstly we'll calculate the constant, right? Constant m heart equals to 1 plus, let me see the equation. Where is the equation? Okay, m heart is equals this. Okay, say equals to, put it here, h heart omega. Okay, h multiple w multiple dt and omega square dt square. So I will calculate omega 2 equals omega dt2 equals dt. So I don't need to calculate them again. Plus 2 multiple dt2 multiple 2. No, beta. Oh, we need beta. Yeah, we need beta. We get beta. 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 So they all have beta. And AV, AA first, AA first. H omega WT dt derivative. H multiple omega multiple dt plus 1 minus beta. So we don't get 1.2, 5 minus beta multiple this one, omega 2 dt2. Yeah. And AV equals to 2h omega 0. 2 h omega plus omega 2 dt. Okay. So then I will start our for loop. For omega for say AGI in AG, I will say okay. But we're not using any the exchange, right? Okay. So I'll say AN equals 0, AN equals 0, DN equals 0. I know some of you are using something more shorter, but I like to use it more traditional way. So I will calculate my F heart equals to AGI plus okay, minus omega 2 DN minus AA multiple AN minus AV VN. Okay, it's very easy to remember. And I will get my A equals to F heart divided by M heart. And yeah, like this. And I get my dA equals to A minus AN. So my V will be Vn plus an multiple dt plus 0.5 multiple dA multiple dt. And my d will equals to dn plus bn multiple dt plus 0.5 multiple an multiple dt2 plus beta dA multiple dt2. Okay, so I will save my, true, A equals to empty, B equals to empty, D equals to empty. So I will A dot append A B dot append B D dot append D. Okay, and an equals to A, bn equals to B, dn equals to D. So I hope there were no wrong. So after all the calculation, I will find out the largest one. So that will be Ag minus A, and SA will becomes the maximum of the absolute of the Z. So I will return SA. Okay. Something wrong? Okay. So TS equals to self dot TS T equals self dot T. Something wrong about this one. New mark. Not defined? Yes, it should be firstly self, and it should be self dot new. Undefined name F. Oh, what is F? What is F? Oh, we don't need F. H omega here, beta dt H. Okay, so let's try this one. Let's try this one. So SA should equals to spec dot response spectrum, which AGDT we don't need self a beta. So beta should be set it before, I think, maybe set it. T also set H also set it, I think. T, oh, we should delete this one. This part we should delete. It's not helping, but it gives us a lot of confusing. We don't need structure setting, we just need something basic setting. And input knet. Okay, oh, something wrong. AG. Oh, yeah, sure. Say wave dot A dt. dt will get dt anywhere. Yeah, it's really silly. Just after input, we see dt equals to this one. Okay, use dt here, dt here. Okay. So let's try. AG. Oh, they cannot do them together. That is very important. So I will say z equals to empty, and z dot appending about agi minus a. So to just refine this will be fine. Hopefully. Still cannot do it for list. Okay. So this one list max. It can do, but I can't do it. Yes. Okay, I should use NPy. Okay, I should use NPy. Yeah. Date NPy equals to NPy dot array that and it can do. It don't need. That'd be fine. Oh, undefined NPy. Oh. Let me get some NPy here. Okay. Better? Okay. This is better. Okay. And I will just show it both. And let's show. You can see response spectrum is very slow. Oh, okay. Yes, because unit is different, right? We need something change unit to go, and we should return because this is in meter square, so we need to return them into just multiple 100. Fine. Yes, you can see the response structure like this, which is very, very strange. No. I think maybe my calculation is wrong somewhere. My calculation must be wrong somewhere, and I cannot find it. I know, but anyway, I just show you how they work through. And we also need compare spectrum. Define compare spectrum. Also, we need something about FFT, right? So if we have that, we will compare compare spectrum. So we will have our FFT Fourier spectrum. Let's say use SciPy FFT, and it will show you how it works. Okay, it just let me import. Import it here. Import. Import. SciPy dot ft dot ft. Okay. So from import ft. Been used, so comment this. So I need a y equals to f of t wave dot a, and I will plot it. Y, of course, to wave dot 2. See. Not working. Variable. It becomes yes, because it becomes complex, so you cannot plot it directly. But we can compare the four. Actually, let me write this into the spectrum part. And compare wave. So say compare wave. So I have a target spectrum, and we have SA. Target spectrum. We have T, and we have AG. Okay, we have arrow, tolerable arrow, self, and so we firstly do something like this, something like this. Right? Here we do self. So FG equals this, and 4 TI in T. Same thing with this. If they are in here, I'll say R goes to SA I equals 0, I equals I plus 1. Oh, later. When the loop is finished. I divide this a t. Sorry, it should be like this. And we will let y I particle r, and j will be the construction part. So we get n minus I. Plus 1, I think. So the vice goes to NP dot conjunction part about y. So when n equals to half n, I think, and when I equals 1, so it should be n becomes n, right? Because if you look at y, when it's 0 is a constant component. When it comes n equals this one, so this one should be the same one. Oh no. Okay, I see. Sorry. No plus 1, just like this. Okay, just like this. So when we compare them, we should evaluate its error. Let's say ER equals to T. So that means that E append by ABS MP dot ABS of R minus 1. Okay, so how if they are becomes 1, R becomes 1, means that they are exactly the same. So minus 1 absolute means how different between R. And we will see the arrow equals to max of E. And sorry, get this one. ET, okay. HE, ET, and H. Beta. Yeah. Beta. So I will find return. So I don't this yet. I will return so the new AG equals to IFT IFT of Y. I will return new AG and also arrow. Okay, so I will delete this part, delete this part, and I will call the function. So let me say AG and ER equals to spike dot in compare spectrum. What we need is this one. So as a target word again here, and T is here, AGTT is here. What's wrong? Undefined name AG. So here is wave.a G. And then we'll plot them. Okay, let me give SA also give them out. SA. SA. Let's say SA0 equals spect compare design spectrum, response spectrum. AG DT T H beta AG. Define I say it's actually here. Okay, let me try. Something wrong? Nothing wrong. Okay. So so I will print ER very large. Let me do it again. So like with A equals this one, so they will be updated again. So theoretically the error should be smaller and smaller. didn't get smaller. So what's wrong? Again. Wow, very large. So let me see what is print E. Let's see what is print E. Yeah, I think some place of the spectrum is wrong about response spectrum. About the response spectrum. So we get omega. Oh, this one. Okay, sorry. I should multiply 2 pi. 2 multiple pi. NP dot pi. Yes. Oh yeah, let's look better. Again. I don't need to plot this anymore. Theoretically, it should become better and better. 0.553. But not. Why? Get the response spectrum. Get a Fourier transform. Getting SAI and TI. We try AG equals to wave dot A. Let's try AG. AG. It should change a little bit, but it didn't change at all. Okay. Okay. Well, true. Oh, let's do a for loop. True. And they will do it again. They will update it again. And if E are smaller than 0.1, this by 4, give them a break. And this time I will do it for loop for I equals I plus 1. If I is larger than 5, I prevent it to it too long, and then plot. Okay, so let's try. Costs a little bit time. Oh, I forgot to print the arrow. Yeah, that's the reason. Okay, I broke it. And maybe show the plot also. Plot also. I will also show the original response spectrum. 0 and yeah. Okay. Okay. Not becoming better at all. Oh, I see. Where's wrong? Why is wrong? So I get AG here, and oh yeah, yes, it's miss. Okay. We stop here because I'm not updating. Yeah. So. If you just read the code, you will get a lot of mistakes. Okay, you can see it's getting better. Or not, whatever, but it's changed somehow, right? Okay, it's getting better and better. Okay, it's lower than 5, so they stopped. So if I change this arrow, standard arrow, smaller and smaller, then it will be becoming better and better, right? So this is the explanation about assignment 4, I think. It's a pretty long video, so let me stop it. Okay, where's my